Why does a tertiary alkyl halide prefer SN1 while primary halide always goes for SN2? If you're always confused between SN1 and SN2 reactions, then this video is for you. Hi, I'm Dr. N. Swati. Today I'll break it down in the simplest way possible with examples, mechanism and clear evidence so that you will never forget this concept. By the way, one more thing I want to tell you students, watch till the end of the video, don't skip the video in between, because at the end I'm going to give you a nutshell of SN1 and SN2 reaction, how you can present in your examination in order to score more marks. You can even print screen those slides also. SN1 and SN2 reactions are two types of nucleophilic substitution reactions of alkyl halides. Before we proceed into the details of SN1 SN2 reactions, let us try to understand the general reaction. So, because these are nucleophilic substitution reactions of alkyl halides, that means the substrate molecule is alkyl halide. So, where the general formula of alkyl halide is Rx. Then it is nucleophile is the attacking group. So, here I have written OH minus, that is hydroxide ion, is a nucleophile. Now what happens here? It is a substitution reaction. Means what? One nucleophile will be taking the position of another nucleophile. Here hydroxide ion being nucleophile in nature, it will take the position of halide ion. So thus OH minus replaces X minus in the alkyl halide structure, so that finally we get alcohols as the products. So there are three different types of alkyl halides are there: primary, secondary, tertiary. So if we take primary alkyl halide, then we will get primary alcohol as the product. Similarly, if we take secondary alcohol, the secondary alcohols upon nucleophilic substitution reactions, they will give secondary alcohols. On the other hand, if we take tertiary alkyl halides as the substrate molecule, in that case we get corresponding tertiary alcohols as the product. So different types of alkyl halides, they give different types of the products upon nucleophilic substitution reaction. So various classes of alkyl halides upon nucleophilic substitution reaction, they give various classes of alcohols. But the attack of nucleophile on these various classes of alkyl halides, it does not occur in similar way. So it mainly occurs in two different ways. So that's why we say nucleophilic substitution reactions exhibit duality of the mechanism. So what are those dual mechanisms? They are nothing but SN1 and SN2 reactions. Okay, now let us try to understand the SN1 and SN2 reactions at much deeper level. So the key features of SN1 reaction. So SN1 is nothing but substitution nucleophilic unimolecular reactions. So they are also known as nucleophilic substitution unimolecular reactions. So we know the meaning of nucleophilic substitution. That means here one nucleophile will be substituted by another nucleophile. Now what is the meaning of unimolecular? So the meaning of unimolecular is here rate determining step involves only one molecule, that is the substrate molecule, alkyl halide. So let us consider the reaction again. So here alkyl halide reacts with nucleophile and we get alcohol as the product. So that means there are two reactants are there in this reaction, primarily alkyl halide and nucleophile. So in a typical unimolecular reaction, if the rate determining step involves only one molecule, that is substrate, means when exactly the nucleophile is going to attack on the alkyl halide, it might be in the next step, right? So that means there are two steps are there in this SN1 reaction. So SN1 involves two steps. Now here if you see the rate of the reaction according to rate law, so the rate determining step involves participation of only one molecule, that is the reactant. So rate is proportional to the concentration of alkyl halide. That means rate at which the alcohol is going to form at the end, it depends on concentration of only alkyl halide. So we can write it as rate equals to K into concentration of alkyl halide. So here K is the rate constant. So here when a reaction, the overall rate depends on concentration of only one molecule, then the reaction is said to proceed with first order kinetics. Hence the kinetics involved in SN1 reaction is first order kinetics. Now coming to the mechanism, here the mechanism of SN1, it involves stable carbocation formation. Now let us deep dive into this mechanism. So the mechanism in SN1 involves two steps. First step is the formation of carbocation and the second step is the nucleophilic attack. So let us consider this particular mechanism by taking tertiary alkyl halide as an example. So here I have taken tertiary butyl chloride. So in the first step, what happens is the carbon halogen bond, that is carbon chlorine bond, undergo heterolysis due to the bond polarity. Okay, so here the bonded pair of electrons will be more attracted by the electronegativity of chlorine. So chlorine will be taking this particular bonded electron pair along with it, and thus it will generate chloride ion. Now what happens, the carbon which is bearing the halogen, because there is deficiency of electron pair, it becomes electron deficient, and that is how a positive charge will be created on this particular carbon, tertiary carbon. Because the positive charge is present on a tertiary carbon, means a carbon which is attached to 3 more carbon atoms. You can see here the central carbon atom is attached to 3 more carbons. So such type of ion is known as tertiary carbocation. Okay, when a carbon is holding the positive charge, that is known as carbocation. Now when that nature of carbon is tertiary in nature, that means when it is in turn attached to 3 more carbons, that is known as tertiary carbocation. So that is how upon dissociation of tertiary butyl chloride here in the first step, there will be formation of tertiary butyl cation as the product. Now once carbocation is formed, immediately the nucleophile attacks the carbocation, because nucleophile bears negative charge and carbocation is having the positive charge. So immediately the positive charge will be attracting the negatively charged nucleophile. So that is how OH will be attached, or it is attacking the positively charged carbon of the carbocation, and that is how we will be finally getting tertiary butyl alcohol as the product. So this is how overall, if you see tertiary butyl chloride, upon nucleophilic substitution reaction, we get tertiary butyl alcohol as the product. Now in these 2 steps, if you see, the rate determining step is the carbocation formation, because how fastly or how easily or how abundantly we are going to get the tertiary butyl alcohol as the product, that depends on how easily we are going to get the corresponding carbocation in the first step. Okay, so the entire rate of the reaction, it depends on how easily or fastly carbocation is going to form in a nucleophilic substitution reaction. That is why this particular step, the first step, is considered to be the rate determining step. So what happens once carbocation is generated, because it is a charged species, immediately it will be attracted by the nucleophile, and the second step is a fast process. Immediately it occurs as soon as the carbocation is formed. Now here one thing we have to understand. So in the first step, as we know that carbocation formation is the main critical step. Now out of the 3 categories of the carbocations we have, that is primary carbocations, secondary carbocations and tertiary carbocations. Which of these carbocations are stable? Okay, because the most stable carbocation will be formed at much easier way, that is very fastly it will be formed. So as we all know that tertiary carbocations are more stable over secondary and primary carbocations. So that is the reason here, whichever the alkyl halide gives more stable carbocation, that means tertiary, will be more reactive towards SN1 reaction. So that is the thumb rule in this particular reaction. Because the mechanism proceeds via carbocation formation, we have to see which of the carbocation is more stable. So that stable carbocation will be formed easily, so that it facilitates the formation of the product in the next step. So it is because of this reason SN1 reaction will be favored always in tertiary alkyl halides when compared with secondary and primary alkyl halides. Now let us consider the evidence for this SN1 reaction with the help of stereochemistry. Now let us consider the stereochemistry in SN1 reactions by considering a chiral molecule. So chiral molecule means a molecule where the central atom is connected to 4 different groups. So if you consider this example, that is 2-bromo-octane as an example, here the central carbon atom is connected to 4 different groups. That is, one side it has hydrogen, the other side bromine, the third side it is having methyl group, and at the top side it is having C6H13 group, that is hexyl group is there. Okay, so such type of carbon is known as chiral carbon. Now in order to understand the optical activity of the molecules, so we have to take a molecule which is having at least one chiral center. So that is the reason this particular example is taken. So here the optical activity wise, if you see this 2-bromo-octane, when the bromide group is on the let us assume on the right hand side, it is considered to be in the LEVO configuration. So LEVO form is denoted with minus symbol and the dextro form is denoted with the plus symbol. So here minus is given, that means it is the LEVO form, LEVO isomer of the 2-bromo-octane. Now, as we know that the SN1 reaction involves carbocation, so let us consider this stereochemistry in the same term. So the first step is carbocation formation, where here carbon bromide bond will be undergoing heterolysis. So as a result of which here the bonded pair of electrons will be taken up by the bromine. So that is how you can see here bromide ion is formed. So with the formation of octyl cation. So here what happens, because this particular chiral carbon, central carbon becomes electron deficient, positive charge will be created. Now you can count the number of carbons. This is first carbon, second carbon, and here 6 carbons are there. So total number of carbons in this saturated chain are 8. So the corresponding alkyl cation is known as octyl cation. Now once octyl cation forms, what happens in the next step? That is a nucleophilic attack. Now there is one more specific thing in this particular reaction you can observe. So in case of 2-bromo-octane, that is the starting molecule, carbon is in sp3 hybridization state. It has 4 different bonds now. So the geometry, if you see, tetrahedral arrangement is there where the carbon is in sp3 hybridization state. Now once it generates the octyl cation, that is the carbocation, look at the configuration of carbon in the carbocation. So here the molecule shifts from a tetrahedral configuration, which it is there previously in 2-bromo-octane, to a trigonal shape. Okay, that means here the configuration will change, that is hybridization state will change. So the hybridization state, it becomes sp2 hybridization. So in the sp2 hybridization, when nucleophile is attacking, it has 2 chances. It can attack from the front side where bromide ion is present previously in the first step, let us say from this side A, and from the back side also there is possibility. The nucleophile can even attack from the back side like this, B. Okay, so in the nucleophilic attack, what happens in the second step is nucleophile can attack from front side. So assume that it is attacking from front side, that means through a side which is previously occupied by the bromide ion. Then what happens? Just you consider the first structure. So you can consider the structure. So you just replace in the front side attack, what happens? Bromide group, finally if you look at the reaction, will be substituted by OH minus group. Okay, so OH minus hydroxide group will be taking the position of bromide. So, and that is how we get 2-octanol. But look at the configuration here. So OH group is exactly taking the position of bromide group. So in the initial compound, the configuration is levoisomer. Okay, so even though 2-bromo-octane is converted to 2-octanol, that means functional group wise change is there, but the arrangement of groups, other groups is same. Okay, and just OH is taking the position of bromine. So that is the reason there is no difference in the configuration or hybridization state of the resulting product. So that is known as retention of configuration. That means starting compound configuration and the product configuration, both are similar, both are levoisomers. Okay, so then the reaction is said to proceed with retention of configuration. Okay, this is when the attack occurs through front side. Okay, on the other hand, the OH minus group, that is nucleophile, can attack from back side also, like in SN2 reaction. So in that back side attack, what happens? OH group will not be attacking from front side where bromine is present. Instead, it will exactly attack on the alkyl halide from a phase or side which is exactly 180 degrees away from the bromide. Okay, and that is how what happens in that case. OH minus group, when it attacks from back side, okay, so hydrogen comes this side and the hexyl group arranges on the top side and OH group takes the back position. And that is how we get finally 2-octanol, okay, with this particular configuration. Now if you compare the configuration of 2-octanol molecule which is formed in the backside attack with the configuration of 2-bromo-octane, that is the starting compound. So here OH group is not directly taking the position of bromide. What is happening? OH is taking hydrogen position. Okay, and hydrogen is taking bromide position. So as a result of which, if OH group is present on right hand side, it is levo form. On the other hand, if OH group is present on left hand side, that is opposite configuration. No? So that is how we get a dextro product. Okay, so here what is happening? The product configuration is exactly opposite to that of the reactant configuration upon backside attack of the nucleophile. So this type of reaction is known as inversion of configuration. So here what happens? Because the resulting carbocation, the hybridization state of the carbon is sp2, which allows for both front side and backside attack of nucleophile. upon front side attack, there will be formation of lever form of 2-octanol where there is retention of configuration, while on the other hand, when the nucleophile attacks from back side, there will be formation of dextro 2-octanol where there is inversion of configuration. That means half of the product we will be getting with retention product and the other product we get the opposite configuration containing product. That means we will be getting here mixture of products, both levo and dextro. So that kind of reaction is known as racemization. So that's why SN1 reaction proceeds with racemization. Now let us quickly learn about the key features of SN2 reaction. Okay, so SN2 is nothing but substitution nucleophilic or nucleophilic substitution bimolecular reaction. 2 means it is bimolecular. Now what is the meaning of bimolecular? So we call it as a bimolecular reaction because here the rate determining step involves 2 molecules. That means alkyl halide and also nucleophile. So here alkyl halide and nucleophile are involving in the same step. What else is there in this reaction? Nothing. Other than solvent, there is no other reactant involved in this step. That means whatever the 2 important reactants are there, if they are participating in one step, means there is no need for the other step to occur. So that is the reason here SN2 reaction involves single step. So if you see the rate of this particular reaction, rate is proportional to concentration of both alkyl halide and nucleophile, that is OH minus ion, because both are involved in the rate determining step. That means overall rate of reaction, it depends on concentration of both of these reactants. So we can write the rate as K into Rx, that is the alkyl halide concentration, multiplied by the concentration of the nucleophile, that is OH minus ion. So in this reaction, as the rate depends on the concentration of 2 reactants, it is said to follow second order kinetics. Now coming to the mechanism, SN2 reaction involves backside attack. Now let us try to understand how this backside attack occurs. So for this, let us consider a primary alkyl halide as an example. So here I have taken ethyl chloride as an example. So here it does not involve 2 steps. That means there is no carbocation intermediate type of the structure formation. Single step occurs here. So nucleophile attacks in that step itself. So here nucleophile will be taking the position of chloride ion. But it is not like a direct hit. So what happens is, because the front side is already occupied, front side of this alkyl group is already occupied by the chloride ion, what happens? The OH group now has no other alternative, but it has to attack from backside. Okay, that is a phase which is 180 degrees away from the halide ion. So that type of attack is known as backside attack. Okay, so as a result of which we get ethyl alcohol as the product. So here this particular SN2 reaction is mainly favored in case of primary alkyl halides. Now what is the reason why primary alkyl halides among the 3 types are more reactive towards SN2? Let us try to understand with examples. So here again, ethyl chloride is an example for primary halide. Why? Because this chlorine is attached to a primary carbon. This first carbon attached to chlorine is primary because it is which in turn is attached to only one carbon. Okay, and isopropyl chloride, another example. So here it is an example for secondary halide because here chlorine is attached to a secondary carbon. Secondary carbon means carbon which in turn attached to 2 more carbons. Okay, so here this carbon is attached to 2 methyl groups. Now again tertiary butyl chloride as an example for tertiary halide because here chlorine is attached to a tertiary carbon. That means carbon which is attached to 3 more carbon atoms is said to be tertiary in nature. If you see, the mechanism involved in SN2 is the backside attack. Now you see the structures of these alkyl halides. Which of these alkyl halides can easily facilitate the backside attack? Okay, that will be more reactive towards the SN2 reactions. Now what happens in case of tertiary butyl halide? Assume that OH minus is coming from backside. Now when it comes from backside, what happens here? Already the backside is occupied with the 3 methyl groups, 3 alkyl groups. Okay, so if the OH minus group nucleophile is pushing one methyl other side also, immediately that place will be taken up by the down methyl group immediately will come and take the position of that pushed methyl group position. It is because surrounded by the one methyl group which is present on the horizontal axis, there are 2 more methyl groups are there. So here the room is very much crowded. This area, backside area, where the nucleophile wants to have an entry is overcrowded with these groups. That is known as steric hindrance. The position, backside position from which the nucleophile wants to attack is hindered due to the bulkier groups, okay, due to the presence of these three alkyl groups in case of tertiary alkyl halides. So that is the reason tertiary alkyl halides reactivity towards SN2 is very, very low. When it comes to the secondary alkyl halide, here also almost the same is the case. Backside attack only, in case of all alkyl halides, as far as it is SN2 reaction. So here there is crowding because of the two methyl groups. Okay, so the crowding is less when compared with tertiary alkyl halides, but still there is crowding. Okay, and when it comes to primary alkyl halides, when nucleophile wants to attack from backside, it has to push only one methyl group. Once it pushes, ho gaya bas khatam. Okay, so it pushes that single methyl group and immediately takes the backside position. So that is how immediately there will be formation of ethyl alcohol. So what happens in case of primary alkyl halide? The room, the area that is backside through which the OH group is trying to attack is less steric crowding is there. Okay, so there is less steric crowding. Because of that reason, primary alkyl halides are more reactive towards the SN2 reaction when compared with other classes of alkyl halides. Now let us try to understand the stereochemistry in SN2 reaction. So let us consider the same example here. 2-bromo-octane, lever form of the 2-bromo-octane. So keep the mechanism in mind always. In SN2, it is backside attack. So what happens? The nucleophile OH minus ion from sodium hydroxide, it will be attacking from backside. Okay, so from backside. Okay, so as a result of which we get 2-octanol as the product here also. Now, if you look at the configuration of 2-octanol, it was noticed through experimentation that the product configuration is dextro, while the reactant configuration, as you are aware, it is lever form. That means here what is happening in this particular mechanism, we are getting a product whose configuration is exactly opposite to that of the reactant. Okay, when it is possible, when there is inversion of configuration, and this is also known as Walden inversion. So when it comes to examination point of view, I want you to cautiously listen about this. So what you can prepare, say for example, if they ask in 2 marks questions to mention about the key features of SN1 reactions, you can just write these points. That is more than enough. Okay, so which I already explained you that what is SN1 stands for, what is the meaning of unimolecular reaction, how many steps are there. Now here, instead of giving a general reaction, it is better you give a specific example, which I already mentioned under mechanism. So when it comes to SN1 reactions, always try to take tertiary alkyl halide as an example. So here tertiary butyl chloride, upon nucleophilic substitution reaction, we get tertiary butyl alcohol as the product. And again, you will mention about the rate here. The rate determining step involves only one molecule. So the rate follows first order kinetics. And what is the mechanism? Just single line. It involves stable carbocation formation. It is because stable carbocation formation is of primary importance here. We have to look into the stability of carbocations. As you are aware, tertiary alkyl halides are more stable here. That is the reason tertiary halides will be more, they will be preferring SN1 reactions, because from tertiary alkyl halides only we can get tertiary carbocations in the rate determining step. And stereochemistry, as you have seen, it involves racemization, okay, because we will be getting here a mixture of both stereoisomers, both levo and dextro isomer will be formed. So you can take screenshot of this particular slide. It will be really useful for you whenever the question is asked to explain about SN1 reactions or the key features of SN1 reactions for 5 marks question or 2 marks question. And also you can use this particular slide information even whenever they ask to compare and contrast or differentiate between SN1 and SN2 reactions as a 5 marks question. So in that case, what you will do, you just make a table, first column SN1 and second column SN2, write all these things whatever are given in this particular slide under first column SN1 reaction. Similarly, key features of the SN2, which I already mentioned earlier, it is a bimolecular reaction. Why it is known as bimolecular reaction? Because 2 reactants are involved. So again here, give a specific example. Like in case of SN2, we always give primary alkyl halide because they are more reactive towards the SN2 reactions, and it involves single step and rate. It involves concentration of, it depends on concentration of both the reactants. So it follows second order kinetics, and the mechanism involved is backside attack. and it is because we have to see which of the alkyl halide can allow for the backside attack. This is the reason why primary alkyl halides are more reactive towards the SN2 because of the less steric crowding. And in case of stereochemistry, because it is backside attack, there will be inversion of configuration or Walden inversion we can observe. Okay, so these are the key features. You can again take a print screen of this. So whenever they ask about key features or explain about SN2 reaction for 2 marks or compare and contrast SN1 and SN2, you can use this slide information. If you want, you just write it in the same matter, give it in the form of sentence formation. That will be more than enough. And a quick recap, SN1 versus SN2 reactions. So SN1 reactions are the unimolecular reactions where they involves 2-step, and here it follows first order kinetics where the rate determining step involves carbocation formation. And the stereochemistry evidence, we have seen that there will be formation of mixture of stereoisomers, so it is known as racemization. And here tertiary alkyl halides will be more preferring SN1 reactions because carbocation formation is the ultimate rate determining step. When it comes to SN2, it is bimolecular reaction involving single step, and it follows second order kinetics because both the reactants will be involving in the rate determining step. And it involves backside attack, and the stereochemistry is Walden inversion. As a result of backside attack, we get a product which is having configuration exactly opposite to that of the reactant. So that's why it is known as inversion of configuration. Alternatively, it is also known as Walden inversion. So most of the times when you get 2 marks, they will ask like what is Walden inversion or explain Walden inversion. You can see such type of questions in your previous question papers also. And always primary alkyl halides are more reactive towards the SN2 reactions. So overall, if you see, SN1 is a unimolecular reaction involving 2 steps. Formation of carbocation will be there, and racemization is the stereochemistry, and they are always tertiary alkyl halides friendly. Coming to SN2, they are biomolecular reactions involving single step, and where the mechanism involved is backside attack, and always primary alkyl halides prefers SN2 reactions. If this video helped you to understand SN1 and SN2 reactions, hit the like button and subscribe my channel for more clear chemistry topics, and share it with your classmates who struggle with organic chemistry. Thanks for watching and stay tuned to my next videos.